Yeah, thank you. Thank you very much, Jürgen. Thanks to all the organizers for having me. So far, it's been a great workshop. I enjoyed every day, many interesting talks. A bit outside of my usual world. So I'm both in the math and the material science department, working in particular on understanding algorithms, errors, these sort of things for first principles methods, so density functional theory in particular. But I'm of course aware that there's people who sit sort of in the scale on top and that use our information, and in particular understanding the interaction between first principles and what comes afterwards. That's also something that I started looking into very recently, and that's sort of my connection to the things that are going on here, and I'm very much looking forward to all the discussions that may still happen. So today I want to talk about basically how to compute derivatives and gradients in density functional theory using a technique that comes from computer science that's called algorithmic differentiation. I will also explain on a high level what this is and how this works. And basically what we can do with this is now that if you take parameters that go into your DFT computation and you look at various output quantity, density, forces, band structures, you can understand how these vary with your choice of parameter. This, for example, allows to design materials in a way that they have certain properties, like, for example, here that the band gap is appropriate. And we are implementing this in a tool called the Density Function Toolkit, DFTK, a Julia-based dense DFT code that is fast and efficient and also allows some hacking. And I will also have a hands-on example on that later in the talk today. Now, of course, this work is not done all by myself, but actually mostly by my two PhD students. Niklas, in particular, has worked on the AD. Bruno was involved to a smaller extent, a bit more on the error estimate side. My group is not too big, and basically that's why I'm collaborating a lot, in particular with mathematicians from various places all over the world. And these basically also have their say in what I'm presenting today. Now, as I said, the point of today, the point of this talk is ab initio materials modeling. So the basic idea is we get some structure, a lump of silicon, we do a computation, and then we ask the question, does this material give me something useful? So for example, in the materials world, could it be used as a solar cell material? Now, what is kind of hidden here is that in the end, what we care about is really the properties. So, we want to predict properties of this material, and then based on this, we actually are able to answer this question, right? So what is properties, or basically how do we compute properties in DFT? That's the first question I want to get into. And so just to put everybody on the same page, this is sort of the notation I will use. Those of you who are familiar with DFT see the familiar Kohn-Sham equations, so nonlinear eigenvalue problem, where the eigenfunctions that come out of this operator are used to build a density, and in itself, the operator depends on that density. So if you're not familiar with that, basically all the information you need for this talk is contained in this equation here. So the idea is we have some self-consistent fixed point density, and if we basically build exactly the potential, therefore the Hamiltonian from this density, we do the whole business of diagonalizing the Hamiltonian, computing the lowest eigenfunctions, building the new density. That's what the F is symbolizing here. And the density we put in is the density we get out. We're done, right? So this is the fixed point equations of Kohn-Sham, the fundamental problem of DFT written in one condensed line. Now, I was talking about properties. How do they relate to all of this? Well, basically, properties is always, to me at least, the response of a material to changing, or of a system to changing external conditions. And I think this is really what connects theory and experiment, because in experiments, that's exactly what you do, right? You somehow tweak the material, you probe the material, and then the response is somehow what you observe, right? So the point here is that this potential function I have been describing on the last page implicitly depends on the number of parameters. So things like, for example, a field strength, that you could apply, but also, of course, structural parameters, what's the structure of my system, or anything like that. And so therefore, if you look at the self-consistent field problem, the self-consistent density that we obtain, that's actually an implicit function of all of these parameters. And now, if you want, mathematically, the properties that we compute are just derivatives with respect to these parameters. So for example, the force could be the derivative of the energy, which is computed from this density with respect to atomic positions, which are contained in these parameters theta, right? So other examples I show here. Point is that being able to compute really the derivative of this guy and being able to do something with it, that's really central and fundamental for physical modeling of materials or molecular systems. But we can go beyond that, right? We can ask questions like, okay, if this theta here is actually a parameter of the DFT model, we can do uncertainty quantification. Like we can understand how my predicted properties depend on actually details of the model. It could be a design parameter, so like a strain or a position. Therefore, we can do this inverse materials design that I was already discussing about. But it could also be, for example, the theta, a parameter of my setup, of my numerics, right? Could be a discretization parameter. And then I get into questions like understanding really the numerical error of a DFT computation. So this is really what I would like to do, and this is really what I would like to do systematically, right? And just to maybe go into a few of these examples in a little bit more detail, let's talk first about inverse materials design. So the idea here would be, as I just said, that our theta is maybe some parameter, strain that we apply to a system. Maybe it's a dopant concentration, if you think again about solar cells. And then what we care about is understand how some quantity of interest, like the band gap, really changes, right? And the band gap, for example, we computed somehow implicitly from the density. And therefore, if we just follow the gradient, right, in order to maybe improve on our quantity of interest with respect to the parameters we can tweak, if we follow this gradient by the chain rule, that's exactly, again, where this derivative of the density pops up, right? So what I'm trying to convince you here is that there's some systematic structure, right? And what sort of boils down to be a central ingredient here is this derivative of the self-consistent density. So this thing that comes out of this implicit equation defined by the self-consistent field problem. Can we do this in practice? So here is something which we have recently done. So here, for example, I'm looking at the relaxed geometries of some simple lattices. So this is basically the optimal lattice constant. So taking by doing this DFT computation and then minimizing the energy with respect to the lattice until I get the minimal energy lattice constant, so the optimal lattice constant, right? So this implies both doing this SCF computations in the inner loop and then on the outer loop another minimization with respect to the structural parameter. And here I'm asking essentially the question, how does this optimal lattice constant as one of these Qs depend on the choice of my DFT functional? And in particular, now I'm going one step further. I'm actually tweaking the DFT functional in order to reduce the optimal lattice constant, or basically to get closer to the experimental lattice constant, right? So here I'm directly training a DFT functional based on experimental data. And that's something that can, for example, be achieved by being able to compute such gradients through an entire DFT workflow. And the same thing, this is what I just showed before. This is the idea that if I'm able to, for example, apply a strain, I'm able to tune the band gap, for example, of a material exactly towards the band gap that I'm interested in. And again, I need derivatives of the band gap with respect to my geometrical parameters to be able to do that. Another example, I mentioned uncertainty propagation, same idea. If we want to get to some quantity of interest, and we're, for example, given some uncertainty in the parameters of a DFT model, there are some DFT setups that allow you to have these kind of uncertainties, then I'm able to propagate from the distribution the uncertainty in my DFT model parameters forward into the distribution of any output quantity of interest, right? And again, this works by applying the chain rule, by realizing if I have some Gaussian normal distribution in my parameters, I get some Gaussian normal in the output, right? So key point again is if I'm able to compute these derivatives, I'm able to do this kind of uncertainty quantification, and we did exactly that. So here we took the BEEF DFT model, which is one of these models that not just gives you basically a prediction of an energy or property, but it has some uncertainty built in, which is exactly encoded in terms of a distribution of the DFT exchange correlation parameters. So same thing, we look at the optimal lattice constant, and we look at basically how the optimal lattice constant distributes with respect to the distribution of these DFT parameters. So that's a way to quantify the uncertainty in the predicted optimal lattice constant that comes out of DFT here. The other values here, I'm not going to explain all the details. That's just for reference, some other methods that people have been using in the field. The takeaway message is that this is fairly similar. So here, the way it works is you do one DFT calculation, you do one calculation of this gradient, which I will explain how to do in just a second, and then you get this uncertainty quantification for your predicted quantities of interest. Yes, question?
Yes. So typically you have, how many Qs do you have for a specific material, I guess? I mean, do you have many Qs?
Yes, indeed, you would.
One or two?
Yeah, you would. I mean, usually, I mean, okay, it depends a little bit on what's your sort of your target in the end. But let's say for a case where you're just given a material and somebody asks what are the properties of this material, then you would have many Qs, right? Indeed. And then, of course, ideally, you don't want to do this just for one Q, but you want to do this for all of them. Yeah, and that's implicitly understood here. Yeah.
And the dimension of theta is?
In this case, the beef is fairly small. It's maybe like 10. Right?
Okay. Is that typical, or it can vary a lot from?
Let's say you can already do a lot with 10, right? So some of like the typical models that are out there that have these uncertainty distributions, the ones that I'm aware of at least, are in that regime. Yeah. But of course, I mean, the grand goal would be to do neural networks, right? And then theta is potentially millions, right? But we're definitely not there yet.
Well, I was asking because so if I think of d capital Q d theta, that's then pretty low dimensional.
Yes.
But the dq d rho and d rho d theta are much higher dimensional.
Yes.
I assume that rho has a high dimensional representation. Yes. So the factorization, I mean, you do d rho d theta once, but it's very high dimensional. So if you didn't have many Qs and the theta is not very high dimensional, I wonder what that buys you. Does that make sense? Or?
Yeah, I get your point. I mean, of course, okay, so I'm not going into all the details here. I'm very happy to discuss about them later or in the questions. But of course, the type of methods you would use to compute these derivatives and how you, for example, do this propagation, what's sort of optimal in terms of cost depends very strongly on the type of quantities that you have. Yeah, and exactly because of these considerations, what intermediates come up and so on and so forth. But there are also some tricks, like, for example, the famous Hellman-Feynman theorem. If you use that cleverly, you can actually avoid some of the difficulties. Again, I'm very happy to go into the details later if you're interested. Okay. All right, so I hope I convinced you that it's interesting to compute these derivatives. But now, of course, having that in your pocket also means that now we want to not just use maybe the few standard derivatives you have in DFT, but we really have a combinatorial problem, right? We really would like to understand all sorts of output quantities, how they vary with respect to all sorts of input quantities, right? So how do we do this? How are we able to do this in this combinatorial problem of potential derivatives? And the key is really that the core is just this derivative of the density and then assembling it in an appropriate and clever way. So let's first talk for 1 second about how actually this derivative of the density is typically computed. That's called density function perturbation theory in the DFT literature. The basic idea is you start from the self-consistent field stationarity condition. Then basically you introduce a variation of the potential, and then you push that variation through to linear order, basically just expanding to linear order both this function f as well as the function v in itself. And then what happens is that you get a so-called kernel. That's the derivative of the potential. And you get here this derivative of the function f, which actually turns out to be an object that people call the independent particle susceptibility, right? And then if you rearrange this problem, basically what you get is an equation that's maybe familiar to some of you. That's exactly some people call it Dyson equation. I think in the Hartree-Fock theory, that's called coupled perturbed, right? So basically all these different names boil down to an equation which looks like this. That's effectively just taking the first order derivative, the first order variation of your self-consistent field problem. And in the end, this is essentially here a linear system that you need to solve by an iterative method. And that's sort of the core, right? So in some sense, what I'm trying to say here is that if we're able to do this, we're able to kind of compute all these derivatives that I was just alluding to. Now, the question is just a question of plumbing it all together. And that's exactly the second ingredient that we need. That's algorithmic differentiation. So how does algorithmic differentiation work? I'll first give you the high-level picture in terms of DFT, and then I'll give you a low-level picture in terms of some toy problems, how this is actually done in code. Now, on the DFT side, the idea here is that a typical computation going from some input parameters, like exchange functional parameters and something like this, to some output quantity of interest, I called this Q before, now I call it A, that basically varies or goes through in 3 steps. You somehow set up your problem based on your parameters, you build the representation of your potential, of your computational setup, of your Hamiltonian, then you actually solve the SCF, and then with the self-consistent density, you compute your quantity of interest, okay? So if we are now just able to step by step take the derivatives, so if we're able to compute the derivative of the potential, then we have all the setup in order to solve our Dyson equation, get the derivative of the density, then we have everything we need to compute this derivative of the quantity of interest, and then we're basically done, right? So the idea is that you go through step by step in your computation along the, basically in the same order as you're going through in the forward pass, as people call it, so when you're actually just computing the quantity of interest in itself. Now, of course, I haven't really told you how then this and this is done. That's exactly what I will do in just a second. But the idea is that this is actually fairly easy, namely by having the implementation, how you compute the potential from your input parameters. This is all a tool based on algorithmic differentiation needs in order to actually also compute the derivative. And I will convince you in that in just a second. The second step, this is what we just derived. We know how to do it. And in the third step, we use the same idea. Since we have the computational graph for computing the quantity of interest from the density and the parameter, then we also are able to compute the derivative. And again, this is something that exactly this algorithmic differentiation enables you to do, and I will convince you of that. So if one is able to do that and assembles all of that, one breaks this combinatorial explosion problem, because this and this is what varies between the different input and output parameters, and that's exactly what this algorithmic differentiation framework takes care of me. Right? So if I have in my, for example, DFT code, an efficient density functional perturbation theory solver, and I couple it with algorithmic differentiation, I'm effectively done. And that's exactly what we have achieved in our recent work. Okay, now before I go into some hands-on examples, let me just mention here, I think this is a bit more than what it sounds or what it looks like in the first point, because what it also helps you is that it somehow separates the concern, right? The computational difficulty, in fact, comes in solving this DFT problem, and that's now a well-isolated box. So people from math can just work on these algorithms, but if we have an improvement there, this is immediately available for all possible derivative computations, right? So for me, this is really key, this algorithmic differentiation, also to, in some sense, separate concern and make it possible for people to work on the code and their advances can compose, right? New derivatives means essentially new physics. New algorithms basically means new mathematics. And this allows an easy way for kind of separating this concern. Okay, let me just add that we are not the first people to do that, but we're the first people to do this in plane wave DFT. And this is essentially something that came later, right? So most codes have basically been built specifically to be differentiable, so to have this AD capabilities. But our code, we just realized at some point that we were able to do that. So the main point of the code was much rather to be able to do mathematical research. Okay, so now I have a few hands-on things I want to show you and hopefully convince you that these things work in practice. But let me pause for just a second if there's more questions at this stage, something that puzzles you.
Maybe
yes.
Words about why plane wave.
Why plane wave? Why, or in some sense, why we do this with plane waves, or why, in some sense, it's new that this has been done with plane waves. Both of it. Okay. Yeah. So. Basically, these codes here, they use Gaussians. So Gaussians have the advantage that the sizes of your matrices and linear algebra representations of your problems are small compared to plane waves. So therefore, Gaussians were much easier to also push through with this algorithmic differentiation, where actually it turns out that memory is often something that you have to be very careful with. That's why, in some sense, for us, there was actually quite a lot of algorithmic development on the side of density functional perturbation theory required that I'm not discussing today in order to be able to even do this for plane waves, right? So this kind of answers what's sort of the additional ingredients here. Now, why plane waves? Why is plane waves interesting for us? Mainly because we wanted to tackle large-scale, so to speak, systems, crystalline systems. And also from the mathematical point of view, I mentioned that this code has primarily been started for mathematical research. There are some things that you can do in plane waves very easily that are difficult, for example, in Gaussians. And one example would be actually error estimation. So I mentioned that we are able to compute the numerical error in the predicted force. Like we're able to tell you if you choose a certain plane wave cutoff, how accurate is your force computation with respect to an infinite cutoff. So that's something you can do in plane waves, but that's very hard to do in Gaussians. So that's also one motivation for us to work on plane waves. Okay.
Electrochemical theory.
Sorry?
Electrochemical theory.
This particular aspect, I don't think is related to Floquet theory, like that basis set error estimation aspect.
No, I'm not talking about. I'm kind of thinking about physics. I mean, if you're trying to really model crystals.
Yes. We are basically trying to look at crystals.
Log waves. Then.
But you could do crystals with Gaussians, right? People are doing that. So in some sense, these things are not, are not contradictory. Yeah. Yes.
Many of the DFT parameters or plane wave parameters are not continuous. You mentioned already energy cutoff. Yeah. So as an exchange is continuously. Yeah. Then my number of plane waves. So how does this enter? So you have something which is, I guess all the examples you give so far are for continuous things. So pseudo-potential is continuous, exchange correlation is continuous. So what about these things?
So plane wave cutoff is a bit of a special one in the sense that the way this is done follows a slightly different technique. We can talk about this later, but yeah. But you're right, and in fact, I think this is the next slide, that there are some catches. And indeed, one of the things is that not everything is differentiable in physics, right? And so you have to be a little bit clever in the sense that, first of all, just because an intermediate is not differentiable doesn't mean that the final thing is not differentiable. In particular, if you do sums over non-differentiable things, you often get back to something differentiable. So it's also a question of how do you formulate your problem. And actually also sometimes if you don't have gradients, like in the rigorous mathematical sense, what will happen, for example, if you have some sort of a branching, these algorithms typically give you one of the gradients, right? So imagine you have a like, just do something very simple. If you have a function which is just the modulus of x, then, and you go through with a typical algorithmic differentiation code, it will either give you this gradient or that gradient. So this is not completely useless, because it actually still tells you something about the function. So my point is that even though mathematically speaking you cannot differentiate it, it can still help you to do an optimization or something like this. And the next point is regularization is very important. So this is something that people also have been in the classical machine learning community exploring. So instead of a maximum, you do a softmax and things like that. So it's really about making it differentiable to an extent, right? But this, I agree with you, it's a tricky point, and we definitely haven't solved this, right? That's in some sense what will be coming in the future, yeah. Okay. All right, so let me demystify a little bit how this algorithmic differentiation actually works. And let me go to this nice notebook here, which hopefully you guys can read. So basically what I want to explain is there are different ways of doing algorithmic differentiation. I will explain so-called forward mode algorithmic differentiation. There's also the so-called reverse mode. I have some slides on this. If you have time later, I'm happy to show it. Okay, so the basic idea of forward mode is, as I said, that we compute both the function value and the derivative at the same time. Okay, so the way this is done is that instead of using just a plain number, you use something that people call a dual number, where basically at the same time you have a float that tracks the value and a float that tracks the derivative. It's as simple as that. And now what you do is you just define yourself new computational routines in order to compose this simultaneous computation of function value and derivative. And that is essentially nothing else but the chain rule. Right? So for example, if we add two of these dual numbers, basically it's the question of computing the derivative of f plus g, right? And that's just the derivative of f of x plus the derivative of g. So basically this means we make a new dual, right? Where we just say we add the values of a and b, and we add the derivatives of a and b. Now the same thing we can of course do for the subtraction, right? So here again we just do it linearly, right? We add the we subtract the values and we subtract the derivatives. Now it gets a little bit more tricky for multiplication, right? Because there the chain rule actually asks us to do a few more things, right? We basically need to do a times the derivative of b, right? So here this is just the this is just the value, right? So the value is always exactly the operation, but for the derivative we now need to do a times b dot delta x, right? So basically this is the f prime times the derivative of g here, plus the derivative of f times the value of g, and then the same thing for this. And because I really don't want to make a mistake, I'm just going to copy this from the solution, but I think you get the idea, right? So basically we just take the chain rule that we already know, and then we implement this on the level of these floating point numbers, okay? Don't know what's happening here. Let's just kill this. Okay, so now we have the rules how to do our composition of this floating point numbers in terms of these dual numbers, basically. Then additionally, we need a way to convert between normal floats and duals. So basically, if we just have a normal real number, that means there's no derivative. So we initialize the derivative part with 0. And then this is basically something that tells Julia here that there's a way to get from normal numbers to dual numbers. So that's all we need actually to already compute derivatives, right? And so for example, I want to compute the derivative of x cubed minus x squared at 2, right? Which if you work it out is just going to be 8. And basically what we do here is we just call our function that we want a derivative. We initialize it with a dual number where the value is exactly the value at which we want to compute the derivative. And the dual part is just 1, right? So we just start with a 1, and then we accumulate as we're going through the computation all the derivative components according to the chain rules that we just implemented, right? And so in the end, therefore, what we want to do here is we want to compute the derivative of the function x cubed plus x squared.
Minus.
Thank you very much. At 2.0. And this indeed gives us a dual number with the first component here is the 4, namely the evaluation of the function at 2. And the second component is the 8, exactly the evaluation of the derivative. Okay, this was nice and dandy, but let's do something cool, right? So now we want to solve Poisson's equation, and we have a density, right? And the density, that one, we will basically introduce a parameter, which is a sigma. That's kind of the width of a Gaussian, okay? So here I take the width of a Gaussian. I have my grid coordinates. I use finite differences here. And then here I just evaluate the Gaussian on the grid. Now, what I do is I just have a function that computes me the potential, right, from the width of the Gaussian, and that is done by solving the linear equation, right? So this backslash operator here is just using Julia's internal functionality to LU decompose the operator, do backward sub and forward sub, and then solve the problem. And I want to solve this on some given density, right? And of course, I am actually interested in understanding how does my potential change as I'm changing this width parameter. Right, so I'm interested in the derivative of this get potential function that solves the linear problem based on this parameter sigma at some, for example, value for sigma. Okay, so this almost works. Why does it not work? Well, it complains about an exponential function not being defined. That's clear. We haven't told our algorithm anything about how differentials are. Exponential functions should be differentiated. So let's quickly do that. Right, so here I'm just implementing what people call a custom rule. So I'm basically giving my algorithmic differentiation framework the information how an exponential function is implemented. And what we also need is a custom rule for the complex conjugation that is actually used within the LU factorization. And if I do that, and I haven't messed things up, which I unfortunately have, then everything should just be working. Okay, does not. That's great. So why does it not work? Ah, yeah, because I was a bit stupid. Okay, now it should work. Okay, there we go. This actually did compute now the potential that comes from a density that depends on this parameter and the change of this potential in particular. And if you don't believe me, here's the solution, here's the derivative. Okay, so what I want to show here is that we coded up our own custom floating point number for AD. This integrates automatically with all the linear algebra operations of Julia, and we were able to immediately use this in a real-world problem. And in particular, we're able to put in, if you want, additional domain-specific information, right? So for example, if we now have a DFT code to differentiate, we know that the derivative of the SCF is solving the density functional perturbation theory, and this is literally how we do it, right? So we just tell the AD system whenever you want to differentiate through an SCF, don't actually go through the steps of the SCF, but just call out to density functional perturbation theory. So going back to my presentation here, right? Essentially when I do this box, that would be just such a custom rule, okay? That I now define for the exponential function. That's how algorithmic differentiation works and how it's actually implemented. Any questions on that? Okay, great. So now let's actually use this in the context of DFT, right? So what I want to understand, or what I want to implement with you now, and is exactly this problem of how do I optimize the band gap of a material to some target that I'm basically giving the material. So the way we do this is first we say, okay, I'm doing this for gallium arsenide, so there's some standard lattice constant. That is the standard gallium arsenide lattice constant. At that level, I can do a DFT band structure computation, and this is what my band structure will look like. Now, the question that we are asking here, or that we would like to understand, is strain engineering. So how does my band gap change under an applied strain? I'm not being very fancy here. I just use a volumetric strain, so I'm basically just compressing and expanding the unit cell. And essentially what I'm carrying here, or what is relevant, is this derivative of the band gap with respect to the strain parameter. So what we do here is we basically just code up a function that computes us the band gap from the strain, and then we will use the algorithmic differentiation tools to compute the derivative. That's essentially the strategy here. So we set up a standard FCC lattice. We use some pseudopotentials. We set up gallium arsenide with the pseudopotentials. We put the standard positions that these atoms have in the unit cell. We set up a DFT model. We will use PBE to do the computation here, put a little bit of smearing to make things easy. And then here comes the function that I've been talking about. So what we do here is we modify our model simply by applying the strain, right? So here is exactly the part that applies this volumetric strain. Then we discretize our model using a rather small cutoff and k-grid. Then we basically call into exactly the self-consistent field computation. This is just to make things a little bit quiet. And then we want to compute the band gap. So we look at the eigenvalues. We look at basically the maximum eigenvalue that is below the Fermi level. So that's the valence band maximum. The smallest eigenvalue that is above the Fermi level. And the difference between them gives us the band gap at the gamma point. Okay, so this is what goes here. This is exactly how you would code it up, right? And then we just say, now please compute me the derivative. And that's it, right? And this is actually how first order the band gap changes with an applied strain. And this indeed goes now through this code, line by line, as we saw it with the AD tools that I just introduced. And when it hits this part here, it will now call the appropriate density function perturbation theory problem, having acquired from the lattice through the values of the plane wave basis to the computation of the Hamiltonian, all of the changes that such a strain will actually do to the numerics and to the physics. And this is then the right-hand side in my density functional perturbation theory problem. Okay, now inverse design is just taking this derivative and doing something with it. for example, one step of the steepest descent, that actually already gets us a bit closer to, let's say, a target value of 0.03 Hartree here for the band gap. But what I in particular want to show you is how nicely this integrates again with the Julia tools for optimization. Because what we do here is we just say, well, let's do a square loss of the band gap with respect to some desired value, right, using the function that we just coded up. And then I call an optimization routine. I deliberately use a quasi-Newton method, so something that needs a derivative that I haven't coded up. And then I just tell Julia, please, if you need any derivatives, just use autodiff in the background. Right? So this will now notice that it needs a derivative for the quasi-Newton BFGS, will automatically invoke forward diff and compute the derivative behind the scenes. And this works. This converges in like 3 iterations. And indeed, we have now optimized our band gap to be exactly the 0.03 that we wanted to achieve. Okay? Yes?
Can you say something about the computational time it takes now to do then the differentiation versus then if I would do semi-finite differences? So for this example, what I would do as, let's say, as standard, let's say, DFT practitioner, I would say, okay, I make one derivative, everything is first order, so I need only to do this calculation once, and then I can just make a linear extrapolation in order to do it. So I need essentially one extra DFT calculation. So how much?
So here what I need to do is for every, if you want for every function and gradient evaluation, I need to do one standard DFT and one response calculation, which asymptotically scales the same as a DFT computation. So from that point of view, in this particular case, you're right that the computational cost will be exactly the same as forward diff. However, the accuracy will not, right? Because I have a slide on that. Remind me if I forget. The accuracy of this method is far better. In particular, it's stable with respect, much more stable with respect to numerical parameters. So I agree that in this particular case, it probably doesn't matter, but certainly you see the difference in other cases. And also, this is in some sense infinite order finite diff, right? So it's not like it's actually doing something, like, you know, in finite differences, if you take 2 points, you're very sensitive to all kinds of problems. And so this is essentially something you can avoid here. Right, so there's a few more points to it than just the actual computational cost.
Okay, 6.
Okay, other questions at this point? If not, I'll go back to the present. Yes?
Similar question, Ray, comparing finite diff to the dimensionality of the strain's one-dimensional, right? So obviously in high dimension you have an advantage in the finite diff, but how does the cost scale with the dimensionality of your perturbation factor?
So in this setup, which is forward diff, the computational cost scales with the number of input parameters, right? So if you have a setup, like here it's one parameter, so it's exactly the cost of your SCF that you also have to pay for the derivative computation. If you have 2 or more, then it just scales with the number of input parameters, like finite diff would do, right? So the cost again scales like finite diff does. Yeah. Okay. Going.
So inside there, you have a dimension of rho that appears in every iteration.
Yeah.
So that's not the dimension of the parameter state. That's the
no.
dimension of representation of rho.
Yes. But that's again. I mean,
right?
Yes, I agree. But the point is that so in this, I mean, the thing is that you cannot be faster than the primal computation in any case.
That's right. Before model also has the factor, and it's also that's right. Yes, yeah. I agree. Yeah.
So in some sense, there's nothing you can do. Okay. All right. Let me quickly say, why do we do all this? So I mentioned that what we are interested in is simulation error and basically being able to propagate things across such a DFT computational pipeline. That's exactly what allows you to do inexact computation without harm. Right? So the point is here to be able to reduce potentially accuracy of models, of numerics, but be able to understand how this impacts your simulation. So that's kind of where this is going in the long run. But let me not spend too much time on this. Let me now talk a little about the density functional toolkit that we have developed in itself. So I mentioned this is a Julia code. It's basically been coming from mathematical research, which means in particular that it's possible to do all kinds of arbitrary models. One dimension, basically you come up with some analytical things, no problem. But at the same time, we can actually treat 1,000 electrons. and we can actually use things like GPUs, not just NVIDIA, also AMD, MPI, and of course algorithmic differentiation, and the whole code is about 10,000 lines, right? So this is a fairly efficient code in a manageable size with a healthy contributor stack. So we have had 50 people in the past, about 3 or 4 regularly contributing. And we don't just have AD, we also have some robust algorithms for SCF that come from the mathematical developments over the past years and numerical error estimates, as I mentioned. And just to give you a flavor of how easy it is really to hack with the code, here's something that I coded up this week. Right? So I realized that what you guys really care about, as soon as you do, for example, implicit solvation, is that you don't just want to solve in the DFT code the standard Hartree computation standard Poisson, but you always have a dielectric that comes in. So I thought, okay, let's just code up a term in DFTK that does this. And so I did, right? So here's some dielectric. Now I actually initialized it to be 0, so that's maybe not the best value to pick. Let's pick a different value. So now it has a little bit of a dielectric on the side of the unit cell here. Then basically here is the implementation of what we call a term. So that's just the metadata that basically has all the information that about the computation. So these are parameters for the inner solver that we need. That's exactly the width of the switching parameter of the error function of the dielectric. We basically evaluate the dielectric. We do what we usually do. We compute these Poisson-Green coefficients. So that's just a solution of the standard Poisson equation. That's just pre-computed. We store this in what we call an instantiated term. So that's the term specific for the basis that you have chosen. And then here comes the actual computation of this extended Poisson equation. So it's probably not the best solver. As I said, I just came up with this in a few minutes I had in the evening. So basically, yeah, we just we come up with an iterative scheme exactly to compute this generalized Poisson equation here. We do a few FFTs, and basically I just take this equation here and implement it. So I hope it's still fairly clear. This one is basically this term. Here we sum over all the, this is the dot product, we sum over all the spatial coordinates. Here I'm computing using FFTs the derivative of the dielectric. Here I'm computing the derivative of the current potential, that's that guy. And here I'm basically assembling everything which is in this inner bracket, okay? And then I'm just doing an iterative scheme to solve this until I'm hopefully converged. And this basically then gives me the potential, and from this I can compute the energy. Okay, so maybe a little quick, but just to give you the idea, here I have just a silicon unit cell. It's a very dumb example. I mean, it's definitely not super useful, I guess. We again do the standard setup that I've already discussed before, and here I just slice in this term, right, that I just defined in this notebook. Instead of the standard Hartree term, I'm still doing PBE. I'm still doing the discretization. I'm still doing the SCF, and basically now the SCF converges, and I can, you already saw it, with this slider, I can interact with this computation because this is a parameter that I'm using inside the notebook. So as I'm basically playing with the slider, the computation should update, which not sure why it's not doing that, but it should be doing that. And the other thing I wanted to show is that this actually works on the GPU. So now you may have seen that here's an architecture parameter. And so if I'm just switching this from CPU to GPU, all the computation is done on the GPU, which actually I'm connected to because that's a GPU in my lab in Lausanne, right? And this includes, I should really emphasize this code, right? This code that we just wrote is compiled to a GPU kernel and executed on the GPU, right? So if you've never done any GPU programming, this is GPU programming, okay? Just saying. Okay, so that's DFTK and how you can hack with it. Now let me just say something.
Can I ask a quick question?
Yes.
First of all, that looks really cool, and I love how fast you can code that, especially for the GPU. And so you could now calculate how the force terms change because you have that extra sigma term in there, right? So that's with a propagation that's pretty straightforward.
In fact, in this, I could do that. I haven't implemented.
I mean, you haven't implemented, but that would be a few lines. That would be pretty straightforward. You don't have to take any derivatives yourself. The code will just do it.
Yes and no. I mean, there's always some rough edges. So I think it's going to be substantially easier than coding it up by hand, because what you can always do is you can use the algorithmic differentiation to just get it done. But then oftentimes what happens is that there are some numerical instabilities, so you need to, or efficiency issues.
That's fine, but you at
the
least get a
point is
unit
these are
test.
localized, and you, with the techniques I mentioned,
structure.
Exactly, you can locally patch that effectively.
Beautiful, thank you.
Exactly. And so I just wanted to say a few words about performance. So recently we did a little bit of study against Quantum Espresso. And while I really have to say that for smaller systems, Quantum Espresso beats us both in CPU and GPU, for larger systems, so this is an aluminum slab with, I think, 20 or 40 atoms, I don't remember. Basically, we are faster than Quantum Espresso, both on the NVIDIA GPU as well as on the CPU. And we are currently working with people from the Swiss Supercomputing Center to improve that performance even further. And just so over the past year or so, we've done quite a bit of incremental improvements, right? And really, let me emphasize, overall, porting our code to the GPU changed about 400 lines of code, right? So it's not that you're really rewriting everything here. It's really that you're identifying, again, similar to the computation of derivatives, that you're identifying the places where it's worth putting in the effort. And there you're really trying to optimize the performance locally without changing too much the code. Okay, let me just emphasize, we have a nice workshop coming up on errors in Lausanne. It's during the LOM program, so I don't think many of you will come, but nevertheless, I wanted to briefly mention it. And this is my last slide. I showed you basically how AD can help to look at errors, to look at error propagation, to look at design. I showed you how this is implemented in this code, which is fast, flexible, and hackable. And basically, it's really designed for multidisciplinary research. And with that, I'm very happy to discuss further during the couple of days to the left. And right now, I'm looking forward to your questions.